Okay, so then we can move on to our next topic. So, so we saw how to think about one-dimensional bound states. Now we want to think about how to think about one-dimensional unbound states. So the most important example of that is scattering from a step potential. Okay, so this is, this will give us intuition about how particles with positive total energy can bounce off some, some potential. So in reality, there are no, step potential because it's a, it's a discontinuous potential. But it's a useful idealization. So suppose that we have some potential like this, and this is, say, the x-axis, and so this is the origin. And suppose that we have a potential which goes like this, right? So, so we approximate such a potential by, say, oh, this is going to be a step potential. Okay, and if you're interested in the, the large time dynamics, then that is good enough. So let's call the region on the left region 1, and region on the right region 2. And what we will do is that we will study the following problem. So, what we will do is that we will study a particle whose average energy, whose hang on. Yeah. Okay. So let's just say a few comments about the classical physics. So let's call this, say, V0, this height. Now, classically, if we have a particle incident on the boundary from the left, if the total energy is less than V0, then the particle would bounce back, right? And there will be some, when it comes over here, there will be some force and the momentum would change and it would go the other way. And if, on the other hand, if E was greater than V naught, then the particle would keep on moving to the right, but with reduced kinetic energy, right? Where kinetic energy would be given by E minus V naught, right? We all know this. But in quantum mechanically, what we'll see is that more strange things happen. So in the quantum case, we'll be interested in the E greater than V naught, the second case, and you can also work out the first case, and it's that's an interesting thing to work out as well. But and it will be exactly accordance to what your intuition tells you. Okay, so is it clear what we're trying to do? Is that we're trying to study how a particle whose average energy is larger than V naught, how it'll behave when it impinges on a step potential from the left. Okay? All right, so I guess you can hear me? Yeah. All right. Okay, so for definiteness, we shall take a Gaussian wave packet that is which is sharply peaked in momentum space. Okay. So because it's sharply peaked in momentum space, it will also have some more or less well-defined energy. The spread in the energy will be very small. Okay, so our initial wave packet is then going to be psi of x at time t0. Let's call it psi I of x, and we can normalize it. It has some spread given by delta. And so we know that it's going to have, if the right. So if I take the average momentum to be, say, k naught, then there will be a phase factor, which is momentum dependent, times e to the power minus x plus a squared divided by 2 delta squared. Okay, so what does this mean? This means that the Gaussian is going to be, the picture is like this. At t equals to 0, at a, we have a Gaussian psi of I, and it's moving in that direction. And this is V naught, and this is X naught. And then what we expect is that after a long, long time, this, wave function will come and, it'll collide with this. And part of this will propagate in that direction because it's a wave and its energy is greater than V naught. But part of it will be reflected back. Okay, so there'll be so this at time much greater than AM by P naught. You can see that this is the only time scale that we have in the problem. So this will be the reflected wave function, or this will be the transmitted. It's actually not wave function, they're probability distribution. The wave function will be the square of the wave function, okay? Okay, so this is what we expect. Is there any questions? Do you get the physical picture?
If the Gaussian is centered at A, shouldn't it be x minus A squared?
Right. So this should be minus. This should be no. This is actually fine because if you look at it, uh, x is so the Gaussian is centered at a, but a here is a negative number, right?
Oh, I see. Okay.
Yeah. Yeah, but you're right. It should be because here, then I should put a minus sign here, right? So yeah, I should put a minus sign there because otherwise the time becomes negative. But yeah, I think there's some kinks to be worked out there. Thanks for pointing that out. Okay, if there are like any big cause for concern, we'll just have to work it out, okay? So I think, putting the minus here suffices because, yeah, this P0 is positive because it's going in the right direction to the right. Okay. Okay, any questions? Any other questions or comments? That was very good. Good observation. Before we move on, let me just tell you something that in many quantum mechanics books, you will find a simplified version of presentation of this, where, instead of taking a Gaussian, what they do is that they take the incident wave to be a momentum eigenstate. Okay, so let's carry on. So since we are assuming that the wave function is sharply peaked in momentum space, this implies that P0 is a more or less well-defined momentum. Okay. Now, and you can show, and this was part of a assignment problem, you can show that the uncertainty in the position and momentum. So you can show that the uncertainty in the position and momentum are given by delta x is essentially the width of the Gaussian divided by square root of 2, and the momentum is given by h bar divided by square root of delta. Okay, so the Gaussian is a kind of special case where the the inequality in the uncertainty principle is saturated. That is, the inequality, the equality sign holds. Because if you remember, the uncertainty principle says that delta x delta p is greater or equal to h bar by 2. But in the case of the Gaussian, for Gaussian wave functions, this is actually delta x delta p is equal to h bar by 2. Okay? All right. So